We have eyes for vision, we have ears for hearing, but we have no organ that we know of that's involved in magnetoreception. It's a complete mystery.
For decades, researchers have tried to answer a simple question with a remarkably complex answer. How do birds find their way?
I had never thought that I would get to a place where we would start understanding the quantum mechanical mechanism that goes on inside the bird.
One of the greatest mysteries in sensory biology is how animals are able to sense the Earth's magnetic field and to use it to navigate.
Researchers have shown that some animals can indeed sense Earth's magnetic field, using it to navigate. But how birds like the European robin detect such a weak field has long baffled biologists.
It's the last sense we effectively know nothing about. And the solution of this problem, I would say, is the greatest holy grail in sensory biology.
And although the answer has remained elusive, researchers have put forward theories that they hope could explain this mystery.
Over 40 years ago, in the late 1970s, a physicist first dreamt up the idea that a light-sensitive molecule might be used by animals to sense the Earth's magnetic field.
This theory proposed that animals could sense magnetic fields using a quantum mechanical phenomenon called radical pairs.
The radical pair hypothesis suggests that you have a light-sensitive molecule, it absorbs light, and in the end you have a radical pair, so two unpaired electrons.
The magnetic spins of this radical pair can take on two states, both pointing in the same direction, a triplet state, or both pointing in opposite directions, a singlet state. The pair swings between these two states, but a magnetic field tips the balance, increasing the likelihood of one of the two.
And it's this change in the balance of the lifetimes of the triplet state relative to the singlet state which is thought to be the basis of magnetoreception.
And there was only one class of molecules that people knew originally could use light to generate radical pairs in plants, and they were called cryptochromes.
So Henrik and his collaborators hunted for these cryptochrome molecules in birds, and since cryptochromes need light to work, they searched specifically in bird eyes.
We found cryptochromes in the eyes of birds, and so did others. And then the big challenge was now, well, how do you now test whether quantum mechanic electron spin-based mechanisms goes on inside the eye of a bird?
The main barrier for the adoption of the cryptochrome hypothesis was that it was proposed by a physicist. So the mechanisms involved were highly quantum mechanical, very, very difficult for biologists to understand.
Henrik and collaborators from biology, physics and quantum chemistry have worked to shed light on this cryptochrome hypothesis.
We needed to have the molecule in isolation to actually measure things on it, because it's very, very difficult to do it inside the eye of a bird. We started trying to make cryptochromes in 2004, and we now have 2021. At the moment, we are the only ones who have these molecules available for testing. And in Oxford, the groups are the only ones who can measure such molecule with the sensitivity needed to see what we have found. Not only could we show that the electrons jump inside the molecule exactly as predicted by the quantum chemists in theory, we could also show that the photochemistry of that radical was actually magnetically sensitive. Now, it's not a hypothesis that this molecule is magnetically sensitive. We can see that it's magnetically sensitive.
The team were also curious how cryptochrome proteins compared between birds that migrate and birds that don't.
We then also made cryptochromes from an extreme non-migratory bird, basically the chicken. And it looks like the cryptochrome 4 from the migratory birds are significantly more magnetically sensitive than the same molecule from a chicken.
Previous work has shown that birds process magnetic field information in the visual region of their brains, and so Henrik and team members believe birds may actually see the Earth's magnetic field.
So maybe it's kind of a shadow on top of whatever else you would be seeing as a bird, but what exactly the bird is seeing, we do not know because we cannot ask the bird.
But the puzzle isn't solved. The team have shown that cryptochromes are indeed magnetically sensitive, but they haven't yet proven that these proteins are the critical ingredient in magnetosensing in birds.
The advances that the authors have made in this study has brought us a long way to understanding how magnetoreception works. There's no question that the study was a spectacular piece of science, but because this is a laboratory study, it's not a study which is being performed on living animals, it's still no actual proof that cryptochromes in general are actually used in magnetosensing.
We are of course going to try to get closer to the natural situation inside the eye of the bird. Things like that would have been utopia before you could actually make the molecule in isolation, and we are very excited about the possibilities there.
I think, having studied quantum mechanics myself years and years ago, I would never have realized then, or even believed, I think, that it would be possible that quantum mechanical effects could be actually housed within the eye of a bird. That is a huge surprise, and that's nothing we learned in quantum mechanics when I was young.